I gave you the intro, the title, and we have a pretty dense program today because we have a great variety of software tools that are very useful in the drug discovery environment. Today I'm going to focus a little bit on structure-based design tools, specifically docking and scoring, and also on the ligand-based design side, where we have the fast feature trees descriptor and also a flexible 3D alignment. And these tools I'm going to show you in the context of a workflow environment, namely Pipeline Pilot. 2-3 months ago we did a seminar like this. There I showed the integration of the same tools in the KNIME workflow in my environment. If you're interested to hear about that, just drop an email. We also have a recording still about this webinar, so that would be an excellent opportunity to just listen to as well. All right, so I'm starting with ligand-based. Show you on a few slides what this is about, and then show you a demo in Pipeline Pilot, actually multiple demos, and then we switch over to the structure-based side, again a few slides introducing the technology and then showing demos. So this is fairly live and interactive and heavy on demos, so bear with me or keep your fingers crossed for me that it all works fine. All right, next slide. The feature trees descriptor. Here's your molecule. This is how it is represented as a feature tree. The feature tree, just for a visual impression, is overlaid here, but in reality, the feature tree does not know nothing about coordinates. It just knows about nodes with certain properties that are the colors here, and connections between nodes according to the underlying topology of the molecule. So if you look at this graph structure of the molecule, which is the feature tree, you notice first of all that rings are always condensed to single nodes. So fused rings are also condensed to nodes according to the connectivity of the underlying structure, but it is very important that there are no circles. That is why this graph structure is called a tree, because that is key for the algorithms that make that descriptor technology very fast. Okay, so we have this graph representation with nodes, colors, and connections. Now, what do we do with it? Or first of all, let me explain the colors. The colors are the physicochemical properties of the underlying structure. So you have these acceptors here, and here you have a donor, an acceptor, and also this is in an aromatic system. How do we now make use of the graph and the colors? That is shown on the next slide. When I put this in perspective or compare it to another molecule, or rather another feature tree representing that other molecule. So I have molecule 1 and molecule 2, both are represented by their feature trees, and now we have this super fast mapping algorithm that maps the nodes of one tree onto the nodes of the other tree, and every mapping here matches one of these little dots with a color onto the dot of the other molecule with another color. That gives me a local similarity. and the normalized sum of all the local similarity gives me the overall feature tree similarity, and that's a global optimum as well. If you do a topology preserved mapping. So we can do that super fast and super accurate because it's really a global optimum. In the next step, after calculating the similarity, we can make further use of this mapping of the nodes of one tree onto the other, and that is illustrated here in a little cartoon by going into the 3D world. When we do that, we generate conformations of molecule 1 and conformations of molecule 2, and then in the first step, we rigidly map the conformations of one molecule onto the conformations of the other molecule. And you see that for this mapping, we use, for this overlay, rigid overlay, we use the mapping of the nodes. So that step is also very fast. Then we take the best scoring mappings, and on the basis of those we do a flexible post-optimization, and that gives us a 3D alignment of the molecules. So every step is really trimmed for high throughput, but in the end we really have a not only a similarity, not only a feature mapping, but if we want to, also a 3D alignment. All these other steps are optional. Okay, with that, LBDD demo, which will follow now. Let me bring up the pipeline pilot window. I have a very simple workflow that incorporates, first of all, the feature trees technology. I should say that these workflows that I use in the presentation today, I will package together, and you get those workflows to try out yourself afterwards. Okay, how does this workflow look like? What kind of nodes does it contain? Well, it starts with molecule readers. I read 2 molecules. Here I happen to load HSP90 ligands, as you can see from this source entry. Just for the sake of the presentation, I add a few molecules, just 100 from the DUD data set, so selected molecule from a benchmark data set. Those flow together, then I pipe them through a node that is called molecule to feature tree. That is that step where we get the feature tree graph calculated. And then in the next node, we compare the feature trees that are coming in through this input port of the node with a query molecule. Here's another mol2 for the query molecule. There are a lot of options, but let's just stick with the details for now. And at the end of the workflow, I have attached a little handy table viewer. We employed Excel for that because it gives us convenient sorting and filtering options right away. This is a free node that is provided with our suite. All right, so reading in molecules, converting them to feature trees, comparing them similarity by wise, and looking at the results in an Excel viewer, and we start that protocol now. So here's the 100 molecules, here's the 9 molecules. they are converted, and then in very little time they are compared, and here pops open my Excel sheet with this results table, which is just the name of the molecule and the similarity value in comparison to our query molecule. And then there is this very handy feature in Pipeline Pilot, in Excel, that allows me to, oops, the wrong tab here, that allows me to automatically filter. I can use this sort in descending order, and right away I see, well, I know the name tags of the known active molecules. Here's the first zinc molecule that comes in the list. So you see an enrichment of the quote-unquote known actives, and some of the other molecules are somewhere down here in the list. Okay, so that was kind of the simplest possible workflow that you could use. Obviously, there's a lot more that can be done, and I prepared that stuff in these other workflows. So, first of all, you may want to make use of this technology while searching much bigger databases. Yeah? On purpose, we don't generate the feature trees on the fly every time anew, but we can do this in a separate step, and we can write out the feature trees to file, so that we need to do this step only once. And I already did that prior to the presentation for 10,000 molecules. Obviously, you can do this for 100,000, a million, or however many you like. The bigger the molecule set, the greater the incentive to do it just once and then make use of these already converted molecules. Yeah? And you can see here, here's a FTrees writer, here's an FTrees reader. Here I read in the already converted molecules. Again, I mix in some molecules. That is my known active set. That is relatively small, so I convert them just on the fly. Both molecules and pre-converted feature trees flow together, and then I do a feature tree similarity calculation, just as in the previous step, except that this time around we do it with a little bigger data set. I start this here, and you see now that we already have converted 1,000. Compare them, it takes not very much time. I do then a top range filter, just the top 20 by feature tree similarity. And then I added another feature tree node. And why do I do that? You will see in a minute. In the first step, I calculated just the BioSolveIT similarity. That's that numerical value that I showed you. But this time around, I wanted to see a bit better what this result looks like. So in a second node with only the top 20, since the calculation takes a little bit longer, I selected as an output property also the so-called BSIT map. And here's in the Excel what this map is about. Let me hide in the Excel some of the columns that are not really important, and then you can see here what this map is all about. The map is a graphical representation of the feature trees mapping. So color-coded, you see here now red maps onto red, green maps onto green, blue onto blue, and so on and so forth. So you can walk your way through the molecule and get an impression of the mapping. Yeah? Obviously, this is trivial if I have the molecule compared to itself with a feature tree similarity of 1, which is the highest possible similarity value. But when I scroll down the list now, I see the other molecules. Yeah? So here is 0.95 as a similarity value, and you see at the tail end here is a little bit of a difference. There's an open chain matched on a 4-membered ring in the other molecule. Yeah? And if I further walk down the list, you see more and more dissimilar molecules. Here, for example, is only a part of the molecule which matches onto the query, and some part of the query molecule is not matched at all. There is nothing on the other molecule that matches well. Yeah? So you get a visual representation of the mapping, as I said, I do this separately only for the top X compounds just to make it faster. And one other trick that I would like to show you is very conveniently you can speed up the process even further when you use the parallel processing options in Pipeline Pilot. So let me crank this number up from 1,000 to 10,000. Yeah, so 10 times as many. And in the feature tree similarity, I go to the implementation tab, and under parallel processing options, I allow the Pipeline Pilot to run 5 processes in parallel, each with a batch size of 1,000. So now, if I run the same protocol again, it ran 19 seconds in the first run. Now if I run this again with 10 times as many molecules, but also multiple processors to be used, you will see that you can really make very efficient use of multiple CPUs on your computer using this. So this step is already completed after 20 seconds. The Excel pops open. That's the same Excel, no change there. But after a total of only 25 seconds, I have now compared 10,000 molecules to my query molecule. All right. So that was still a relatively simple workflow. Let me go to the third one, the third demo. Again, it follows a similar strategy. I make use of the feature trees reader node here to read previously converted feature tree files. I do a calculation of the feature tree similarity, and now instead of just showing you the 2D depictions of the mappings, I go to 3D. So here I use this strategy that I had showed on the slides to generate the conformers, overlay the conformers in the first step rigidly, and then with a post-processing step for fine-tuning in 3D the alignment really. And then I have multiple output nodes, and we look into that as this workflow is running. So the output nodes are, of course, here my Excel sheet, but I also wanted to show you the synergies between technologies from us and from others. So here, for example, is the DS Visualizer node. That's a free software package for academics from Axeris, a general purpose visualization package, particularly if you are already using Pipeline Pilot, then you may be interested to use also this visualizer. My Excel sheet looks again relatively similar to before, to the one before, with the exception that all of a sudden I have multiple similarity data columns here, not only the feature tree similarity, but also a 3D overlap, another 3D alignment score, and finally a normalized 3D score. That is, depending on the use that you have, you may want to prefer more on a normalized score, which just ranges from -1 to 1, or use the exact FlexX 3D similarity score, or this other one. You have 3 flavors of score. They are obviously heavily correlated. I suggest find out for yourself which one is best suitable. Alongside of the Excel sheet, here this DS Visualizer viewer popped open with the molecules. I have the last one in the table, which is the bound ligand, my known active. If I lock the visibility here in the table, then I have a quite convenient way to scroll through the table here. Let me first change the color of this one here. Wait a second. Display style. I just want to make this relatively simple for viewing. Okay, so I have this light green here now for my query molecule, and the other one overlaid. And now you have here the different scores.
Die Stummschaltung ist aktiviert.
You have the
Die
different
Stummschaltung
scores.
ist
You see the
aufgehoben.
overlay, and you can skim now through the different solutions. Wait a second. I need to go to the top of the table, and then the next, and the next, and the next. So side by side, you see the score, and you can judge for yourself how much you like or dislike one or the other alignment. And also, as you skim through the table, you get a sense for these different overlap scores that are provided by the software. So I know this is really going through all this stuff in a rush, but the main purpose of this was I wanted to show you that with this technology, oops, wrong slide, you can get the feature trees mapping, the 2D depictions, and the 3D alignment, all quite conveniently in the Pipeline Pilot environment and you can put it together with other nodes provided from Pipeline Pilot, or through Pipeline Pilot, let me say so. So this is the ligand-based discovery part of the presentation, and I would suggest if somebody has a question at this point about this particular stuff, go ahead and raise your question. Otherwise, I'll switch over then to structure-based, the structure-based technology. Anybody has a question, type it in or unmute you and yourself and raise the question. Otherwise, I'm going to continue with structure-based stuff. Okay, I don't see a question coming up. If something remains unanswered, yeah, we can still talk about that at the end of the conference. Okay, the structure-based side, also I don't want to go in a whole lot of detail. Probably quite a few people in the audience will know FlexX, which is a docking software that has been around for many years. It's an excellent program. 2 years ago at an ACS meeting, there was a grand competition about about all the different docking technologies. And this slide here kind of summarizes very concisely the performance of our Docker compared to the other Dockers. So you can see here that in 93% of the cases on a benchmark data set, we can dock compounds under 2 angstroms deviation from the crystal structure. And if we go further down to 1 angstrom, which is really high accuracy docking, it is still more than 3/4 of the cases, 77% that we can dock with this accuracy. So the redocking is really excellent. And the virtual screening, which is the other big application area for a docking program, pipe a lot of compounds through and skim off the top in hope for finding the most likely candidates, the most potent compounds, is really difficult to compare. So this runs on the DUD benchmark data set that is 40 targets. And as you will know from all these docking publications, the performance of a docking program is very much dependent on the particular target. So one program may work very well on one target and not very well on another target. You have a high range of, let's say, performance scores, and it really depends on the target how well you do. So that is why we, in order to come to a comparison, we came up with this box plot idea, which shows us the range from the maximum to the minimum, and also the majority of the cases. That's this middle 2/4 of the performance cases. And here you can see the median and also the top, these center quarters of the AUC values, that's the enrichment values, on the 40 targets in this benchmark data set. And you see that the programs more or less score all the same. the median of FlexX is really head-to-head with the glide docking median performance and also the range of the box plot. But I have to admit, so is it for the others. My conclusion from this is, there are docking programs that work a little bit worse, but the other docking programs, they are really good performers. No clear winner here, and FlexX is certainly among the best that participated here in this competition. So that is FlexX, and the other software is a more recent development from our side. That's the so-called Hyde scoring function. And rather than explaining to you the technology, since I want to focus rather on the demo, I just give you this one picture summary of the Hyde scoring function, which we also associate very much with visual affinities. And you'll see in a second what we mean by that. So the one outstanding feature of Hyde is that we can map scores onto the atoms. So each atom has an individual contribution to the score, and I will show you a few exemplar cases. The color coding is as follows. It is red if it is a positive delta G, so unfavorable contribution. It is green for a negative delta G, so a favorable contribution, and it ranges from green over white, which is no contribution, to red. Yeah? And let's just look at a few exemplar cases. Here is an acceptor sitting opposite to another acceptor on the ligand side. Both these atoms pay a penalty for being desolvated and not making a hydrogen bond. So that is a total desolvation cost, as we call it, of 10.6 kilojoule per mole, which is very much in agreement with the literature about strengths of hydrogen bonds. But it is also very intuitive. Yeah, everybody knows that it's not a good idea to bury a hydrogen bonder in the binding interface without making an interaction, and worse so if you have two pointing to each other. Yeah. The second one is here an aromatic carbon sitting in an aromatic groove on the protein side, and both these aromatic carbons on the ligand side and on the receptor side, on the protein side, contribute favorably a total desolvation gain. The water is happy to be freed from this surface, is minus 7.2 kilojoule per mole, so a significant favorable score. And last but not least, we obviously also have these hydrogen bonding situations here. It's a mixed situation in that for the polar atoms we have to pay a desolvation penalty, but then the interaction gives us back an energy as well. So in an ideal scenario, when the hydrogen bond is really perfect, you have a little favorable scoring contribution. So the desolvation penalty is overcompensated. But you also notice this is not dramatic. Yeah? It's a small favorable scoring contribution. So the real driving force is here. Yeah? The desolvation gain from burying hydrophobic surface, and the real driving force for making those hydrogen bonds is the desolvation cost. So if you miss that hydrogen bonding interaction and bury the polar atoms, then you pay the penalty. So that in just one slide is the Hyde scoring function, and obviously now we like to put the FlexX docking and Hyde together. And that is time now for the docking demo. That is the SBDD demo. And now the workflow becomes a little more complex. I start again with a molecule reader, then I have a docking node here, and since docking calculations, as you can imagine, are a little more time consuming than these descriptor calculations, I just initiate the process here already while I explain the protocol. After the docking, or let's look at the docking node first. The parameters of the docking node is 10 poses per docking, so 10 poses per molecule that is docked. So that means if I dock some 18 compounds here, it is again my HSP19 ligands that I had previously compiled from these ligand-based searches. I used them as an input and calculate 10 dockings per compound. That means I end up with 180. And rather than scoring them all, I already want to filter here. I use a threshold of -21 using the FlexX docking score. So that is a very rough empirical scoring function used there in FlexX. And I use the remaining molecules, that is 49, have a better score than -21 and plug them into the Hyde scorer. And then afterwards I sort the data by their Hyde score, so the best Hyde score first. And then I condense the data table with a merge node that is done such that I identify the molecules that have the same name, so same name, multiple docking poses, and then I keep only the first of the ones with the same name. And since I have sorted by Hyde score, I keep by definition the one with the best Hyde score. So that's a very simple way. Here's my table already. That is a very simple way to shrink down multiple docking poses after the scoring to just look at the top scoring pose. Yeah? Because you don't want to look at all those other variants, just condense it down to the essential minimum. And again, I pop it open in an Excel viewer. You saw that pop up already. I write it out as an SD file, and I also plug the results into the DS Visualizer node. And that DS Visualizer, let me grab that node, grab that software here.
Christian, 15 more minutes.
Okay. Okay. Here is DS Visualizer result, and somehow now it is open. So I have, as you see here, a PDB reader node that loads in the same protein, and I stick that into the DS visualizer as well. And here I have my table of the top 5. Now I'm not a very I'm not an expert user, let me say, of DS Visualizer, but I know a few things that you can do, so I can copy that whole structure here and plug it into the other table. And then I have the view of my protein together with the ligand. And again, I want to change the colors here in the visualization so that it is relatively easy to compare the original structure with the docking poses. And you see that result here, at least I hope that you can see it reasonably well, that all in green structure is the protein with the bound ligand, and that atom color-coded structure is the small molecule. If I now lock the view of the protein, I can again use this table scrolling feature and skim through the solutions. And here is the first one from the zinc database. So that was one of the high scorers in from the ligand-based search that I just dropped in here. And you see that also in 3D it docks reasonably well. It has a significantly lower Hyde score compared to the top scoring ones, which are native compounds to this protein. But still, you know, it is a reasonably high score to look at the compound. And this would be one technology to do it. But really, in order to complete my story, I need to close the window here. All right. And I want to go over one other topic that I haven't told you the details about, and that is how does the protein come into play in these nodes. Yeah, it's obviously that the ligands loaded are docked, but how does the protein come in? Well, the protein comes in through as a LBDD project file. And I named that here $target. That's a neat little feature. If you use a parameter in multiple nodes, then you can just declare this parameter on the workflow. So I give the name of that docking input file just once. I call the parameter target, for example. I'm free to call it anything. And then I can use that target thing here and also in the Hyde scorer. This way I make sure that I use really one and the same file for the docking and the scoring part. So that's a little utility thing I think that might be useful in general. And how do I generate a LBDD project file? That is the last step it would be the first step in the process, but the last step here to complete my story. I load in a protein, 3R40 PDB is the protein, into LBDD, and then I walk through a few steps of receptor preparation. I start with loading the PDB file, making sure here that I really have the right one. In the next step, I select a chain that is containing my binding site. In the next step, I select the compound that really defines the binding site, and there are a few other ways how you can define a binding site. The easiest is to take that bound ligand as a so-called reference ligand, and then everything around it is automatically carved out as the definition of the binding site. The next step adds all the protons on the ligand side and on the protein side, and that is a very clever algorithm that is able to do that here in just a few seconds, assigning the different states of the residues, rotating the water molecules, and also protonating my small molecule so that it is about as good as you can do by hand. Clever heuristics at work here. Then in that next step, you can have a metal coordination definition, but we don't have metal atoms here, so we are already at the finish line. Click on that button. Then a surface is calculated, and the definition of my binding site is completed. So I can switch on the surface and make sure that everything is fine here. Now I save this to file, and then I can stick this file into Python Pilot, and that is what I just did in the Python Pilot protocol, right? What I generate is a so-called project file for 3R40 FXX, that's the PDB code, and .fxx, and I stick that into as a parameter into the docking node, $target, and into the scoring node as a target. And I wanted to show one other thing. As you saw here, I also wrote out the solutions in an SD file. Obviously, I can also use this visualization here to look at the results. And in order to do so, I open the Molecule tab, load a library of molecules, now let me look for the date. So I generated an SD file, date of today, so it must be this one. So that are my 5 ligands. For each one of them, just the top scoring pose. And if I have them in here, I can also get that visualization that I showed you in the PowerPoint presentation. I switch to the Hyde widget in the LBDD GUI, and then select a compound from the library, and then my ligand is visualized here with this red and green color coding that you have seen previously on that transparency. So here you can see now how this molecule fits in the active site, and you can see the the red and green contributions. Now, just to make my story complete, I select that one compound. I mean, these are known binders. This one is the first one from the zinc database, so that would be now the hypothetical scenario of a new compound that you may purchase. And as you can see here, it fits reasonably well into the active site. If I switch off the view with atom colors, I see that I have quite a few favorable contributions here. Scoring contributions, let me drop the surface and it becomes a little more clear even. There's just this one atom which is colored red. Let's see what that is. That is an OH group on the compound that is unhappy here to be desolvated because it doesn't make an interaction. So the desolvation penalty on this here, gives it the unfavorable contribution. Then you can even go a step further and edit the molecule and, for example, delete this atom. Now you are in optimization mode, so to speak, and interactively you can rescore the change that you just did and play around with the structure and really figure out. See, you gained a little more in score even, and now pretty much everything is green. You could tweak that ligand further and do kind of an interactive brainstorming session of possible modifications on the compound. So, as a recap, switching back to my slides, in the first part I showed you the ligand-based design tools. That's essentially a descriptor technology for fast similarity calculations, browsing through many molecules, and you can use that further to visualize those similarities in 2D depictions, and you can also overlay the molecules in 3D. And then in the 3D world, you can also work with proteins. Obviously, you can do the routine task of docking, and you can use our latest development, which is this scoring function called Hyde, and you can either use another external visualization tool, or you can use our GUI to make most effective use of the interactive GUI. I showed you the parallelization feature in Pipeline Pilot, which is quite convenient. Just crank up the number of processes and run the job so and so much faster. And I showed you that there is obviously interplay between nodes from us and nodes from others that are very synergistic. And with that, I'm through with my presentation. Time's already also almost over, and I would